Hello again. This time around, we're going to take a look at how to find missing sides and angles of triangles. So this is another application of trigonometry. So we're going to look at some real world application. So how to use these trigonometric ratios um, and the angles that correspond to them, how to use those to measure real world quantities and problem solve in the real world. So um, we're going to take a look at what's called right triangle trigonometry, the law of sines, and the law of cosines. All of these. Um, so this whole setup right here, this is, you can think of it as finding unknown sides and angles of triangles. That's essentially what this is. This is all going to be about, is how do you find unknown sides and angles of triangles. Okay, so let's start with a different way to think of the trig ratio. So sometimes in real world application, you don't ever need to worry about an angle that's bigger than 90 degrees. And if you don't need to worry about an angle bigger than 90 degrees, you don't need the unit circle definitions of the trig ratios. So if you only are going to work with angles that are bigger than 0 degrees but less than 90 degrees, so basically any angle that would fit inside a right triangle. So of course a right triangle has a 90-degree angle, but the other two angles are between 0 and 90. If those are the only angles you're ever going to be concerned with in your application, your situation, then you don't need to use the unit circle definition. Now you can, by the way, there's nothing wrong with the unit circle definition, but you don't need it. So you could get rid of the coordinate plane completely and the circle and just deal with a right triangle. So let's say we have a right triangle. So let me draw a right triangle here. So here's a right triangle. And then let's say this is an angle theta. So I'll have that angle up there be theta. So this side, this is what we call the opposite leg. That's the opposite leg. And then this one right here is what we call the adjacent leg. And then, of course, it's a right triangle, so this is always the hypotenuse. Okay. So a little bit of Euclidean geometry here. So whatever the angle is, so like I've got this angle up here kind of at the top of my right triangle. So if you look, these are the sides that make up the angle. So the leg that's not used to make up the angle is called the opposite leg. And then here are those legs, here are the sides of my angle again. If the leg is one of the sides that's used to make up the angle, then it's called the adjacent leg. And then, of course, the hypotenuse is always the hypotenuse. It's always the longest side of the right triangle. So by using this language, we don't need the coordinate plane. I don't need an X. I don't need a Y. I don't need a radius because there's no circle. I don't need any of that. I can just use this language instead. So using this language, I can define the trig ratios again. I can say, you know what? Sine of that angle is the opposite leg divided by the hypotenuse. Cosine of that angle is the adjacent leg divided by the hypotenuse. Tangent is the opposite leg over the adjacent leg. Now, of course, what we mean is their lengths, their measures, right? So what is the length? We mean the length of the opposite side and the length of the hypotenuse, or the measure of. That's what we mean when we write opposite, hypotenuse, or adjacent. We mean how long they are, because, right, the trig ratios we know by now are actual real numbers. So the ratios of two numbers. So we're talking about their measure. Now nothing changes here. If I want cosecant, I just simply do the reciprocal of sine. And if I want secant, I just simply do the reciprocal of cosine. And if I want cotangent, I just simply do the reciprocal of tangent. So that doesn't change, but there's no need to, I mean, again, you don't really need to worry about those three. If you just remember these three and which ones are reciprocals, you're good to go. You're good to go. Now, by the way, you know, the triangle can be drawn however. So let's say you've got a triangle that looks like this. Let's say you've drawn it like this on your paper. So there's the right angle. And let's say this is the angle down here that we're interested in. So this would be the opposite leg, and this would be the adjacent leg, and then this would be the hypotenuse, as always. That doesn't change. It's always the longest side across from 90. So again, you can draw the triangle however you want. It doesn't have to be in what's called standard position because there is no coordinate plane. There is no unit circle. We don't have to worry about it. It's all based off these triangles. Now, you might be thinking, wait a minute, don't I already have definitions for these that work? And I just spent a lot of time using them and I got really good at it. True, this definition is not in conflict with the other one. It actually works just fine with the other one. So if I do the unit circle definition again, so let's draw the unit circle. Here's the unit circle. Then let me put an angle on there. Here's an angle. There's a right triangle. This is x, this is y, this is 1 or r, right? Doesn't have to be the unit circle. So this coordinate is x, y. But look, the definition we just wrote down using this right triangle without the unit circle, it's the same thing. If this is my angle right here, this is the opposite side. So y is opposite, x is adjacent, and then, of course, the other side's the hypotenuse. And all of these are the same. So for example, sine of that angle is y over r, or opposite over hypotenuse. Cosine is x over r, which would be adjacent over hypotenuse. They're the exact same ratio. All we've done is removed the unit circle, removed the coordinate plane, so we don't need to use an x and a y and a radius. We don't need any of that. So why did we have the unit circle? What was the point of it? Because the unit circle allows us to define the trig ratios for any size angle. Your angles can be bigger than 90 degrees. They can be negative. They can be in the hundreds of degrees. We can do radians. It just allows for, it's a more universal definition. It encompasses a lot more situations. The right triangle approach only allows us to do angles that are acute. So they have to be between 0 and 90. That's it. The only angles that are allowed are right here. The only angles that can go right here are angles between 0 and 90. But it turns out, you know, often, those are the only measurements we're interested in. So that's why this is useful. So let's practice. These aren't real world problems to start out with. Let's just practice with these definitions. So find the values of all 6 trig functions for the angle alpha. So I've got this angle alpha here. One leg is 5. The hypotenuse is 7. So this would be the opposite side over here, right? Because it's the leg that's not used to draw the angle alpha. So here's the angle alpha. I don't use that side. Therefore, it's the opposite side. Okay, let's give this a whirl. So this would be the opposite side of that angle alpha. Let's do Pythagorean Theorem to find it. So 7 squared plus, or equals, sorry, it's the longest side. 7 squared equals the opposite side length squared plus 5 squared. So 49 minus 25. So 49 minus 25, that'd be what, 24? 24? So the opposite side is going to have a length of principal square root of 24, which is what, 4 and 6, so 2 square root 6. 2 square root 6. Okay, so this is 2 square root 6 over here. So let's try it. That'd be 4 times 6 is 24, plus 25 is 49, which is 7 squared. All right, so I think we're good. Okay, now we want all the trig ratios. So for example, sine of that angle is opposite over hypotenuse, right? This is opposite over hypotenuse. It's the opposite side over the hypotenuse. Cosine of whatever that angle is the adjacent over the hypotenuse. Tangent is the opposite over the adjacent. Right, that's opposite over adjacent. Now to get the other three, just do the reciprocals. So cosecant of whatever that angle is 7 over 2 root 6, which is 7 root 6 over 12. And then secant is 7/5. And then cotangent is 5 over 2 square root of 6, which is 5 square root of 6 over 12. So there's all 6 ratios. Now, I never did figure out what that angle is. We could do some inverse trig and get the angle, right, if we wanted to. We weren't asked to. But that angle is simply inverse sine of 2 square root 6 over 7. And then we could type that into our calculator and get an angle for it. But we weren't asked to. We were asked to find the trig ratios for the angle. So we didn't need to know the angle, just what the trig ratios were for it. So this is meant to just be practice with which ones are opposite, adjacent, and which ratios are which. All right, so the next one we are being asked to find the angle. So I know all 3 sides. I know the hypotenuse is 12, this is 8, and this is 4 root 5. So if I label everything, this is the opposite side. This is the adjacent side. And this is the hypotenuse. Now, I can use any trig ratio here. It does not matter. So for example, I could say sine of that angle is opposite over hypotenuse. Or if I wanted to, I could say, okay, no, cosine is adjacent over hypotenuse, if I'd rather do that. Or I could say, no, tangent is opposite over adjacent. It doesn't matter which one I do. I'm doing more than I have to here. To get that angle, I just simply do the inverse. So inverse sine of 4 root 5 over 12, and then I can type that into a calculator, which I'll do here in a sec. What I'm showing you here is it doesn't matter which one I do. So like if I do inverse cosine of 8/12, I'm going to get the same angle. It'll give me the angle I desire. So it does not matter which one I do. So let's go ahead and type one of those in the calculator and see what that angle is. So we get just slightly bigger than 48 degrees. But again, it wouldn't have mattered. I could have typed this in to get the same thing, or I could have done inverse tangent. Again, whatever ratio you're comfortable with and whatever you're willing to type into the calculator, you're good to go. So the angle we were asked to find is just slightly bigger than 48 degrees. So now we can combine these two ideas to find unknown sides and angles of any right triangle. So here's a right triangle where I don't know either leg, and I only know one of its acute angles, which is 12.7. So right off the bat, I know that the angle theta is just going to be 90 minus 12.7. I don't know why I wrote that so tiny. So the other acute angle is going to be 77.3 degrees. Okay, so so you can label that now, right? So this is going to be 77.3 degrees, right? We know that now. And let's go find the two legs. And again, you have options. Don't feel like there's only one way to do this. If you think of a different way, using our new definition for the trig ratios, then by all means do it. So for example, I look at this and I see this angle. I see this is the opposite side, and I see this is the hypotenuse. So opposite hypotenuse is sine. So I think, okay, sine of 12.7 degrees is opposite over hypotenuse. So that leg is, if I cross multiply, this is just a proportion, that leg is going to be sine of 12.7 degrees times 22. So I'm going to get out a calculator, make sure you're in degree mode, and then I'm going to ask the calculator what, and the direction said around to the 10th, so that's 4.8. So I know that this is 4.8. I've rounded it though, I've rounded it. So I got to keep that in mind. So I'd like not to, if I don't have to use that measurement, I would rather not use that measurement. That way I keep some accuracy on the other leg. So when I go to find leg B, I'd say, okay, here's this angle. This is the adjacent. This is the hypotenuse. So cosine of 12.7 is adjacent over hypotenuse. So that leg is 22 times cosine of 12.7 degrees. So that leg, after asking my calculator, is 21.5 units of length. So we needed to find that one, and that one. Those are the three missing measurements for that triangle. So let's see, now we're ready to take a look at a real world application. And remember, at this point in mathematics, these real world problems aren't all that contrived. These are, far more realistic than, say, the stuff you looked at in your first year algebra course, where you had trains that were always going 88 miles an hour. Well, no train is always going 88 miles an hour, so that's not realistic. These are slightly more realistic. There's not a lot that we're kind of fudging here. This is a pretty plausible situation. We have a surveyor, that was trying to measure the width of a river at a particular point, right? So this is an overhead view. That's the way I'm going to draw this. So let's say you've got a river. There's my river. And you're trying to find the width at a particular point. So like, let's say right here, you're trying to find this width, W. So that's the distance. Maybe you're going to build a bridge, right? You're going to build a bridge across that. So you need to know what the width of that, how far across the river it is, so you know that the bridge is long enough to span the river at that point. So this surveyor places her instrument called a transit, points it directly across, and then she turns 90 degrees and begins to walk, and she walks 200 meters. Then she looks back at the same point. So she points her instrument at this same location over here, and using her instrument can figure out that this is 20 degrees. And this is a doable thing. There are instruments that find the angle between two locations. And we want to find the width of that river. So I know that this leg is 200, this leg is W, and this is 20 degrees. Well, using my right triangle definition for my trig functions, I can actually get that width pretty accurately, as accurate as my other measurements are. So that's the opposite leg. This is the adjacent leg. So tangent of 20 degrees is opposite over adjacent, right? I don't know the hypotenuse. This is the hypotenuse, and I don't know it. I don't know the length of it. So I can't use sine or cosine because I don't know the hypotenuse. But I know tangents ratio is opposite over adjacent. So the width is going to be whatever 200 times tangent of 20 degrees is. So the width is going to be approximately, again, asking the calculator, 72.794 meters. So if you're going to build a bridge, it better be at least that. But now you have an idea, right? You're going to build it a little bit longer, so it's on firm ground on either side. But you don't want to overdo it, right? You might be sitting there thinking, well, I just would have built a 150-meter long bridge, and then I know it'll go over it. Well, sure, but now you're wasting material because you didn't need to go that long of a bridge. So 72.794. I didn't really say what around, so I just went to 3 decimal places. And now we know the width of the river at that point. Let's try another one here. We got a straight trail leading from a particular hotel with that elevation going to an overlook. All right, so we're going to do, this time we're going to do a side view. So let's say this is the hotel. And you're going to walk up to an overlook that's at a higher elevation, right? So that's why I'm drawing it up here, because it's at a higher elevation. And the length of that trail is 14,100 feet. That's in feet. What is the inclination of the trail? So I need to know this angle. And the only other thing they've given me is elevation. So as you may or may not remember from, for me, 6th grade, Mrs. Saucer, love you, Mrs. Saucer, we, an elevation is basically the distance above sea level. So the hotel's elevation was 8,000 feet, and the scenic overlook had an elevation of, so this distance, of 11,000. Grabbed the wrong number there. Gotta check myself. 11,000. So that's 11,000. Okay, and the trail's 14,100. All right, got it. And let's see, we want to know that angle. Well, I know the hypotenuse of this right triangle, so I have this right triangle here. I know its hypotenuse, and I actually know this leg. This leg right here is 3,000 because it's 11,000 from the sea to the overlook and 8,000 from the sea to the hotel. So it's 3,000 from here to here. Just subtract those. That's the angle or the segment addition. Postulate or theorem, I've already forgot, from geometry. I think we're ready to go. That would be the opposite leg, and that'd be the hypotenuse. So sine of that angle is opposite over hypotenuse. That's definitely a ratio less than 1, as it should be. So that angle is going to be inverse sine of whatever 3,000 over 14,100 is. Of course, we're going to have to round. So that is 12.28 degrees. That's the inclination of that particular trail that leads up there. Now, why would anyone want to know that? Well, I mean, depending on your age, or if you're, maybe you're in a wheelchair or you have an assistance device that helps you get around. I mean, you kind of need to know that that trail is at a 12.28 degree inclination. It's going to be a lot of work to get up that trail to go to that overlook. So useful information to be able to tell people that at the hotel. All right, next up is just a bit of vocab in case, because everybody comes to this class having passed through different courses with different teachers and instruction. So just in case you've never heard of an angle of elevation or an angle of depression, I want to make sure that we're familiar with that language. So what is an angle of elevation? So let's say there is a person or thing. Doesn't have to be a person, but I'm going to draw a stick figure. It could be a thing, right? It could be like a camera. You have a person or a thing, okay? So you want to know where horizontal would be. So you would start from horizontal. So anytime you have an angle of elevation or an angle of depression, you always want to kind of like your standard position, kind of like your base of where everything's going to start is horizontal. So what if that person was looking horizontally? An angle of elevation is where you look upward from horizontal. So this, let's call that theta. That would be an angle of elevation because you are looking above horizontal. Well, if you look downward, so let's say you look downward, I'm going to just call that alpha just to use a different variable than theta. This is called an angle of depression. So if you look downward from horizontal, angle of depression, upward from horizontal, angle of elevation. It's that simple. You got to start from horizontal though. You have to start from horizontal. Basically, we need a way that when a situation is described to someone, we all would draw it the same way. Without that, it just gets confusing, right? It's like, well, where's that angle at? Is that the angle between here and here? Or is it the angle between here and here? Placement of angles becomes very, very complicated if you don't use this type of language or you standardize it in some way, I guess is what I mean. All right, so let's give it a try. So meteorologists find the height of a cloud using an instrument called a ceilometer, maybe? I've never said that word or heard it said correctly. I'm kind of guessing there. It directs a vertical beam of light to the cloud base, and then a special detector scans the cloud base for the light. At a particular airport, this meter was employed to find the height of the cloud cover. It is set up so that the light detector is 300 feet from the projector. If the angle of elevation from the light detector to the base of the cloud is 75, what is the height of the cloud cover? Okay, so let's see if we can't get this drawn. So we've got the light detector and the projector 300 feet apart. All right, so we're going to do a side view here. It's going to be a side view. So here's the ground. So here is the detector, and here is the projector. And we are trying to find the height of a cloud. There's my cloud. It's a beautiful cloud, isn't it? I don't feel like drawing a cloud. So this is the base of the cloud cover. Okay. All right, let's see what it says. These are 300 feet apart. So the light detector is 300 feet. If the angle of elevation from the light detector to the base of the cloud. So here's the detector. You're going to aim it up at the base of the cloud to try to find the light that is being projected by this, right? It's going to shine light up to the base of the cloud. And then this detector is going to try to go find that light way up there. So it says the angle of elevation. So I got to start from horizontal and then go upward. And that's 75 degrees. And we're supposed to find the height of the cloud cover. In other words, I want to know this distance. So tangent of 75 degrees is opposite over adjacent. So all I got to do now is do 300 feet times tangent of 75 degrees. Again, asking the calculator. It turns out the cloud cover is 1,119, and if we want to round a little bit, so almost 1,120 feet in the air to where the clouds start. Let's try another one here. We got a particular building has a statue atop it. From street level, 2 observations are taken 400 feet from the center of the building. Okay. So here's the ground. Here's the center of the building. So the building has some height, right? So there's going to be some height to that building. So this would be the height of the building right here. And then there's a statue on top of it, centered on top of it. So it'd be right here. This would be the height of the statue. So this is the height for the building. and this is the height of the statue. All right, so 400 feet away. So 400 feet away. Well, that's terrible handwriting. By the way, this is a side view. 400 feet away, we're going to take some sightings. Basically, we're going to look at the building. And it says the angle of elevation to the base of the statue is 55.1. So if I start at horizontal and then look at the base of the statue, it's 55.1 degrees. So that'd be this angle. But if I look at the top of the statue, which would be way up here, that angle is 56.5 degrees. So I've got two angles here. I've got this one and I've got this one. All right. What is the height of the statue? So what I desire is this right here, height of that statue. So I'm going to do two right triangles. I'm going to do a big right triangle. The big right triangle would be 56.5 degrees. This one. And then this is 400. So using color, it'd be this right triangle. That's what I just drew over here. That one. And then I'm going to do a smaller right triangle, the smaller one where this is 400. This is 55.1. And then the way this breaks down is the statue's like right here. Like there's the statue right there. And then again, if I just use some color, it'd be like those match up. That'd be this right there. It's kind of what I'm looking at. So let's do the small right triangle first. I'm going to do this one first. So that would be the opposite and adjacent. So tangent of 55.1 degrees is, I don't feel like writing opposite. I'd rather just use a variable. So let's call this x. And we'll call the statue's height y. Or let's use h for height of the statue. Let's do that for height of the statue. So it'd be opposite over adjacent. So then I'd do my proportion, use my calculator. And we get 573.3866 feet. So that's how tall the building is. That's how tall the building is. But I want to know the height of that statue, so I got to go figure that out. So let's do the bigger right triangle. The bigger right triangle would be tangent of 56.5, which would then be x plus h, right? That's that whole side. So it'd be x plus h all over 400. So now I'm just going to cross multiply and subtract the 500. So h is going to be, so the height of the statue, again, using the calculator. That statue is about almost 31 feet. Almost 31 feet. Not quite, but almost. All right, next up, we got a lighthouse here. So we got this lighthouse that's 117 feet high on a hill, 245 feet high. So its beam is 362 feet above the sea level. Okay. Brochure states the light can be seen on the horizon about 26 miles distant. Is that accurate? All right, again, let's do a side view here. So let's say this is the Earth's crust, and because we got to involve the horizon here, then let's say this would be the center of the Earth. So There's the radius of the Earth, which I think we're going to need the radius of the Earth, so I'll have to look it up. It's 3,000 some miles. I'll have to look that up here in just a sec. And then we have the lighthouse, right? So then the lighthouse extends on top of that. So this little distance here that's the 362 feet, but the center of the Earth to that point is going to be in miles. So I want to switch this to miles. So in miles, that would be 362 over 5280 miles. Now, I want miles because from the center of the Earth to the Earth's crust, that's the radius of the Earth. That's going to be in miles, which I need to look up. So that's 3,960 miles. So if I draw a right triangle, see if I can do this here. Might not be perfect. There's a right triangle. And then this distance, I'm going to call, that's the length of a circle, so an arc length, that's S. That is S. So basically this would be the light from the lighthouse. That's what that line segment would represent. That's the light from the lighthouse. So if you were here, you could see the light. If you were here, you cannot see that light. That light would not make it to you, is what this picture is, showing us, the situation. And let's see, we know that this distance is 3,960 miles also because it is the radius of the circle. We just don't know the leg of that right triangle. So I basically know adjacent and hypotenuse. Okay, so cosine of that angle is adjacent divided by hypotenuse. And then I can get that angle. That angle is going to be inverse cosine of whatever this is, which of course I'm going to use a calculator for. So it's about 0.33715. When it's so tiny, I'm going to use a lot of decimals here. Degrees, and if we want radians, radians is 0.0058844, I believe. I typed in my calculator correct. Okay, so now we want to know this arc length S. So arc length is the radius of the circle times the angle, central angle in radians. By the way, you don't have to know off the top of your head the radius of the Earth. It's not something you have to know off the top of your head. And arc length, the arc length formula using radians, I don't think you guys did that in your Euclidean geometry course. You had a different arc length formula that uses degrees, which is okay. You can use that one, but the arc length formula for radians is much simpler. It's just the radius times the angle in radians. So S is going to be 3,960 miles times 0.0058844. Let's see what that's going to be. That's going to be 23.3 miles. Now, by the way, this would be what are called statute miles, miles that don't account for the curvature of the Earth. Nautical miles account for the curvature of the Earth. But in this case, S is 23 miles. That's not a huge distance on the surface of our planet. So I don't know if the curvature there is going to matter a whole lot here. So we're just going to do statute miles instead of doing nautical miles. But just know that nautical miles would be less than this. Nautical miles are longer than statute miles. So it'd be a little bit short of a distance here if we did nautical miles. Either way, this brochure says that if you're 26 miles away, so if you're 26 miles away, you can see the light from this lighthouse, but you can't. The light starts to disappear at about 23.3 miles away. So the brochure is a bit off. So I don't know if they're trying to lie or deceive, but this estimate's not very good. Turns out you're not gonna be able to see that light much past 23 miles away from that lighthouse. Okay, so kind of like angle of elevation and angle of depression. In case you've never talked, any navigation at all or talked about bearings at all, we're going to introduce nautical bearings. So I by no means am I a ship captain. I don't fly airplanes. So I am not an expert when it comes to all the different ways to navigate earth and sea. But one way it can be done, I'm going to show you one way that it can be done. I know of one other way. I know of two different ways, but there's probably more out there. I'm going to show you one. And it's my understanding that these are the type of bearings that are typically done out on large bodies of water, like the ocean. So I could be wrong. So if I'm wrong, feel free to let me know. But the way bearings work is basically you need a point at which you are going to determine your heading. So right here would be the moment the object's heading is determined. Now, so this, you'd be looking at a map, of course, right? This would be on a map, right? Here's some land, right? So here's some water. Here's some land right here. So you're out at sea and you're like, all right, I'm going to go this way. So there's a way to basically, you can't just saying I'm going to go this way is not very helpful to anyone else. So we all need an agreed upon way to like tell someone else where you are headed, on this water. And here's how this is one way this is handled. So the moment you determine your heading, the moment you do that, that's a fixed point. Then from that point, here is north, here is east, here is south, then here is west. So let's say from that point, you've decided that you're going to head in this direction. That's the direction you are going to travel. You're going to travel along that line right there. So what is that? There's what's called a bearing that goes with that. And here's how that's determined. Let's say that the angle between north and your direction of travel, let's say that angle is 40 degrees. Then your bearing would be north, because that's where we started, 40 degrees towards the east. Towards the east. North 40 degrees towards the east. Let's say that's one possibility. Let's say instead you decide to go in this direction. Let's say you decide to go this way. So this is your direction of travel. And let's say this angle right here measures out to be 72.6 degrees. So your bearing that you would report to other people is that you're going south 72.6 degrees towards the west. So you always start from north or south. Basically, are you traveling in a northerly direction or a southerly direction? And then is that direction towards the east or towards the west, and by what angle? By telling someone this bearing, they can get out a map, find where you started from, draw out the bearing, and then get your approximate path of travel is the idea. So let's try another one. It always starts from north or south, though. Always start from north or south. Right? That's important. Always begins with north or south. That's important. So let's say you were traveling along this line here. Well, maybe this angle is 21 degrees. Because again, you got to start from north. That's the idea, start from north. So this could be north 21 degrees towards the west. North 21 degrees towards the west. So anyone with a map in your exact location when you determined your bearing could go find and basically the path you're traveling along and could locate you in a time of need, for example. All right, let's give it a whirl. So a passenger jet takes off from a runway that has a bearing of north 20 degrees towards the east. Okay, so here's where they take off. There's takeoff. So they leave the ground and start traveling in a certain direction. So north and south, east and west, right there. So it's north 20 degrees towards the east. North 20 degrees towards the east. So that'd be like in here somewhere. North 20 degrees towards the east. Specifically, this is 20 degrees because this is north and this is east. After flying for 1 mile, the pilot turns 90 degrees to head toward the northwest. Northwest. Okay, so they're going to so I know you guys can't do this easily on your paper. I apologize. Should have planned ahead. But I'm basically going to give myself some room to adjust this picture. So now they want to turn and head towards the northwest. So at some point, say right here, they're going to turn and head towards the northwest, but they make a 90-degree turn. So this is 90 degrees. I don't know why I can't draw that very well. We know that this distance is 1 mile. And then they do 2 miles in that direction. So basically, if that's 1, then this would be 2. Oops. Let's say that would be 2. What bearing should the control tower use to locate the aircraft? So in other words, what if something happened and they needed to locate that aircraft? So here's where the aircraft is now, and the control tower would need to locate it. So we're going to need this angle right here, starting from north, right? We got to start from north. Well, let's see if we can't figure that out. So I'm ultimately going to want to know that angle right there, theta. So this bearing is north theta degrees towards the west. I just don't know what theta is. It says now, but not really. I just need to figure out what theta is. Okay, let's do this big right triangle. So I'm going to draw that big right triangle. So it looks like this. Here's that big right triangle. I'm going to scale it down a bit. This is 2, this is 1. I'm going to call this whole angle right here alpha. But remember, alpha is, it's the angle inside the triangle. It's not theta. It's not the angle I actually want. It's the whole big giant angle in the triangle. It's this angle right here. So opposite adjacent. So tangent of alpha is opposite over adjacent. So alpha, we use inverse tangent here, get that? 63.43 degrees. But I know that this chunk of it is 20. This chunk of it is 20, so all I got to do is subtract to get theta. So theta is going to be 63.43 degrees minus 20. So it'd be 43.43 degrees. So they should use a bearing of north 43.43 degrees towards the west to locate that airplane at that precise moment. All right, that should be enough for our right triangle definition for the trig ratios. Next up is going to be the